Hello everyone. Let us know about memory regions, heap, stack as part of the memory management chapter. The stack memory and heap memory are one of the important concepts of memory management in Java. When we write a program or the instructions that we write in a program, these are stored in a memory block called code. The region where the allocated variables are stored is called static memory, or the name static comes from these variables not changing. We have a stack memory. When we make method calls, it adds local variables to the stack, and when we return a method call, it removes the elements on the stack. This could be related to adding and removing objects like a pile of dishes when you add or remove dishes from a pile. And we have a heap storage. You can refer to heap memory or storage as a pool of memory you have, and you allocate memory from that whenever you are creating new objects. Let's say you're creating a new string. The memory for new string reference will be taken out from the pool or heap memory and allocated to it. As you can see in the picture, when you are creating a new string, the memory is being allocated in the heap, and the variable s within the stack memory is referencing this string. The stack memory, last in, first out, is a memory access technique that the stack data structure uses. Let's see what kind of things are placed inside a stack. The arguments of a function call are stored within a stack. The registers of calling functions are also saved on the stack. All the local data that you initialize or declare within a method or a function are also allocated inside a stack. The stack is also a place where the function leaves the result for a calling function. Let's say you want to add two numbers, and when you call the method, it's being added to the stack, and when you return the method, the written data or the written value, which is the addition of two numbers, is also being popped out from the stack and written to the calling function. Stack is the data structure that supports recursive function calls. Here in the slide we have two images. The one on the right side, as you can see, is a stack data structure which follows last in first out memory access strategy. We push objects into the stack, and as the memory or the elements grow in the stack, whenever like a return call of the function will pop the object from the top of the stack and return to the calling function. This is a last in first out memory access technique. And on the left hand side we have another image, function called stack, where we have the functions being added to the stack. The main function is the first one that is being added, and the main function, let's say main function calls the function foo, and this could be a recursive call, and foo calls itself, and then a new object is being created and pushed into the stack, and this might go on as this is a recursive call. Heap space, as I said earlier, heap is kind of a pool of memory that you have and will be utilized whenever a new object is created. This does not follow any discipline like last in and first out. So all the dynamic allocated data structures that survive the function calls are being allocated from the heap. As I said, the new object or the new keyword that we use in Java to create new objects basically takes memory from the heap. In multi-threaded environments, all the threads and processes are going to share the heap memory, so it is always recommended to remove any unwanted variables or free up the space for other processes to use this heap storage efficiently. Here is an overview of Java stack memory and heap space. These are the virtual addresses that you have on the left hand side, and on the right hand side you have the stack and the heap, which grow in size, expand and shrink as the program executes. And we have the static block and the program, which is the instructions or the code that you write. Let's see a comparison between Java heap space and stack memory. Stack is used in parts one at a time during execution of a thread, whereas heap, the entire application uses heap space during the runtime. Often, the size of a stack has limitations depending upon the OS and is usually smaller than the heap space. And heap space does not have a size limit. The storage. Stack memory stores only primitive variables and references to objects that are created in heap space, as we have seen earlier in the image. All the new created objects are stored in the heap space, and these objects are being referenced from the stack. The order of stack memory. It's accessed using last in first out memory allocation system. And heap, the memory is accessed by complex memory management techniques that might include the following: young generation, old or tenured generation, and permanent generation. Let's see some security worries we have in happens heap and stack. There is no default initialization for stack variables, so when you are reading uninitialized local variables, you can read memory content used in earlier function calls. There is only finite stack space. As I said, depending upon the OS we are using, the stack space is limited, it's finite. A function call may fail because there is no more memory. This could happen when you have infinite loop, or not a loop, basically an infinite recursive call going on, and there was some bug which is preventing it from being stopped. Then this could be a case of stack space being full and you cannot use it anymore, and the program throws an exception and the program stops abruptly, which is always not good. In highly safety or secure critical code, you want to ensure that this cannot happen, or handle it in a safe way such that your program execution does not stop. The stack mixes program data and control data. This is a stack buffer overflow problem. If you want, you could search the internet for the stack buffer overflow problem. The problem is basically when you have an array allocated some buffer within the stack and you are accessing beyond the limits of the allocated data structure, then you are basically accessing the next element in the stack, and thereby if you change it, it's going to corrupt the address of the next element in the stack, which is a problem. You can just go and look up for stack buffer overflow over the internet for more information. Thank you for listening to this video.